Hi everyone, and welcome to this series, NoSQL for the Relationally Minded. In this episode, we'll explore graph databases, how they work internally, and what we can use them for. I want to start out this talk by clarifying something controversial, that relational databases are not relational, they actually just store lists of data. Let's jump in with an example from the canonical Northwind dataset. Here we've got two tables, one with product information and the other with orders. If this was a traditional relational database management system, we would say that these two tables have a relationship via a foreign key. But let's look at what actually is happening within the database to enforce that. In reality, the database doesn't store the relationship per se, it just stores two tables of data. The foreign key leans on two columns in these tables, one in the source and one in the target. When we add a new row to the target table, the database does a seek operation on the source table to assert the value entered is present. And this can be expensive, especially if there is a lot of data in the source table. This is tolerable compute when we're appending new data. It's tough but manageable. But gets much worse when we need to leverage the foreign key to join the data. Here's a simple query joining two tables. And because the database doesn't store the relationships themselves, it instead loads both source and target columns through memory and matches the rows to produce a result set. Now, traditional databases are optimized towards this and can scan through these large sets of data reasonably quickly. But if we look closely, there's two problems now surfacing. The first is that, as a design, relational schemas usually try for normalized data, which means that the majority of useful queries lean on at least a few joins to provide their value. And so, rather than like this, queries can end up more like this, spanning multiple tables, and each join adding exponential scanning workload to the query. So although relational databases are optimized, the very nature of relational databases requires joins on these lists of tables, and that's the irony. The more you normalize the data, the harder your system has to work. The second problem is that it's not just multiple tables nowadays, but modern applications tend to deal with huge data also. In our example, we might reasonably expect thousands of customer rows, millions of orders, and tens of millions of order items. And so the work to scan these rows to join them in queries is immense. And the underlying issue here is not just the amount of work, but that relational databases are themselves just table stores and don't store relationships. They just store tables of data and indexes, and this could be considered a design flaw in that most of the data they typically hold needs to be related before it's of use. This cartoon from Gaping Void illustrates it perfectly. We can store information, but it's only when we join the dots together that we start to create value. The value comes from the relationships between the data, and so it's really valuable to store these relationships. So how would it work out if we did this? If speed and value both can come from storing the relationships in our data, what would our schema look like if we had the relationships in there too? Let's try it out. I'll assume for this you're familiar with relational database schemas. And so let's start off with the schema for the Northwind database. To change this to one where we store the relationships as real database entities, the first thing we do is find the foreign keys and replace them with named relationships that we store in the database. Next, we identify the join tables, and we replace these with rich, direct relationships too. Then we're done. It might sound a bit pie in the sky to store the relationships, but this is actually how we design graph databases. These entities and richer relationships now represent what would be our baseline graph schema for the Northwind database. Not far from the traditional relational schema, but a bit simpler. And so we can add them like this to our graph database. You can see it's not a large leap from a traditional relational schema, but some of the data helped to be stored directly on the relationships instead. If we're modeling things with richer information on the relationships, let's look at an even more relationship-oriented way to model the data. Here's an even simpler example relational database of flights and bookings. Migrating this to a graph database schema, storing both data and relationships, we know that each table can roughly be translated to a node in a graph database, and each foreign key translated to a relationship. The difference is that now the relationships are actual things in our database, and so we can store both directionality and additional data on them. Typically, in domain-driven design, we consider the nodes as nouns in our business domain, and the relationships as the prepositions, conjunctions, or verbs. Adjectives are stored as properties on the nouns, and adverbs are properties on the relationships. So in this example domain, our nouns are the people, bookings, flights, airports, and etc. And our verbs are how they interact with each other. Simplifying this down, we can visualize it like this. In advanced scenarios, each node can be a union type, and so represent several overlapping values. But for now, just think of them like this. Each node stores your nouns and associated data, and each relationship the verbs and their associated data. So now we've covered how data is both faster and richer, easier to understand, and capable of more easily holding inferred information through storing the relationships. But how do we build graph databases internally to do this? Let's dive deeper and explore how a data store for graph data works under the hood. If we were to build our own graph database, one of the first things we've got to understand is why traditional relational databases don't store the relations themselves. Because then we can work out how to solve it from a more informed point of view. And you might be surprised, but one of the main reasons relational databases can't efficiently store relationships is because of the variable size of the row data. I'll try to explain. When a relational database stores data on disk, it stores it within what are called pages. These pages are a fixed size to speed traversal. If, for example, we wanted to go to page, say, 6, we could work out exactly which partition, sector, and index it was on the disk mathematically and jump straight to it, since all data pages are constrained to be the same size. When you're configuring a relational database, it's important to consider this page size setting so that, ideally, an integer number of rows fits on each page. Reality doesn't work like this though, and row data size is usually variable. And so, in cases when a row is too big to fit on a single page, or where a page is not completely filled, then the database will try to use the remaining page space to store partial rows, fragmented across different pages. This is acceptable, as we can periodically defragment rows. What it means is that our database cannot store relations, because any direct pointer to a row's data position would need to be updated as sibling rows change size or when defragmentation occurs, and this would make writes very slow. So how do we solve this? We know now that the thing we need to address to store relations in any kind of efficient way is to make all row data fixed size, and we can do this by storing a fixed amount of data on the node. And so in graph databases, we limit it to only a handful of fixed size values. The system ID for the node, whether or not the node has been soft deleted, and we'll cover that in a minute, a single reference to a linked list collection of relationships associated to the node, and we'll cover this shortly too, another reference to the types represented on the node, a single reference to a linked list of the properties, and that's it, nothing else. This means that every node is the same size, and every node is tiny. All other property data can be stored off-node in a separate linked list store, which has different optimizations from the node traversal store. The same goes for the types of data of each node, and for the lists of pointers to relationships originating or terminating at each node. So the node store only contains contiguous tiny pieces of data, all at a predictable size, holding the IDs, a flag, and a few pointers. Now, we can see that scanning or searching through our data might end up slower because the data isn't on the nodes themselves. But let's come back to this later when we deal with indexes. For now, consider this design of fixed-size nodes as a necessary trade-off when storing relationships, as it allows the relationships to reference the nodes directly rather than via a foreign table scan or seek. And so we're storing relationships. How does this design play out to those? We can apply the same storage design to them by making them a fixed-size storage unit too. This way, when we need to load a relationship from a node's reference to it, we can find it immediately on disk because we can mathematically calculate its position exactly. What are the fixed fields we store on a relationship then? We store its system ID, a contiguous long integer, same as for nodes, its soft delete flag, a single type name. In a logical graph, relationships, unlike nodes, only have a single type name, a memory pointer to the nodes at the start and end of the relationship, a single reference to the properties, and that's it, nothing else. And so every relationship on disk is the same size, and every relationship is tiny, no matter how many properties are attached to it. All other data is stored by reference, same as for nodes, in the more classic linked list store. Now I mentioned earlier about deletion. When you delete a node or relationship, it would be slow to then reshuffle all the existing pointers. So what we do instead is delete the reference property data and type data and relationship reference for the node in question, and then set fixed size node and relationship data to empty. Leave them as holes. When new data is written to the store, you can write over these holes with the new data, like this. This means that, unlike relational databases, in graph databases, you'll find the system indexes for nodes and relationships are reused after deletion. And this is important, as it means, unlike relational databases, you don't want to use node IDs as a reference directly, because they will be reused after deletion. If you need a unique ID for each node, which you probably will, in most cases you'll need to add your own instead as part of the property data for each node, and include it in an index. And so the last component in graph databases to speak about is indexes. If you want to find a subset of nodes, your criteria will usually start via the property data. Property data is usually held in a linked list serial format and spans multiple pages, so it's not very efficient to scan. So, like document databases, we project the property data we need to search on into indexes. Then, when we need to find the data, we can query the appropriate index. The index points directly to the immovable fixed-size node entries, and these nodes, in turn, have in-memory pointers directly to their relationship linked lists. And these relationships have direct in-memory pointers to their reference nodes. And so traversing between the two is really, really fast. This ability to traverse at high speed between nodes via direct pointers to and from relationships, because of their fixed size, by offloading all property data into secondary storage, allows graph databases to keep traversal as the topmost design concern, and so can scale to in-memory pointer traversal across millions or billions of nodes because of the fixed size much more simply than a traditional database. This new way of storing data and of considering data as drawing more value from its relationships rather than the data values is a fundamental shift in the database paradigm. This, in turn, raises an opportunity to look at the API we use to interact with such a database. Going back to our example, we can see that the classic API provided through SQL is oriented towards the flat tables of data, and somewhat ironically, much less so around the relationships. The format returned by a SQL query like this is flattened and tabular, even if it's drawing from nested or related data. The results lose all the richness of relationships and supply only flattened data. If you want to use the relationships, you will have to include multiple flattened tables in your result set and then join them in memory on the client to model the relationships. So the results are flattened and lose the relationships. And what about the query itself? Surely the query language is still largely about joins, right? Let's take an example of SQL to explore how SQL is actually not well oriented toward describing relationships, but instead itself oriented towards columns of tabular data. Let's take a relationship first query. What would the SQL look like if we needed to traverse multiple relationships? Let's take an example from an HR application. Find all the direct reports and count how many they manage up to 3 levels down. The SQL for this query, taken from a Berkeley computer science course, looks like this. You can collapse it a little using recursion, but it gets even harder to read. So we can see that the cognitive load that SQL adds while leveraging relationships can be high. And what if we took a fresh approach, where the language instead was focused on relationships both simply and primarily? SQL as a language focuses on the flattened result table foremost in its select clause, and then details the source tables and joins in the subsequent from clause that feeds the data in. It works, but it's clunky, because at all points the context remains flat tables, rather than data with inherent relationships. So let's redesign SQL to focus instead on relationships first, and extrapolate out the data second. We'll use the same query, but with a new relationship-focused language. The hard part here is traversing the relationships of who manages people and limiting them. We could write it like this. Here we find all people and the people they manage up to 3 deep. because our new paradigm of relationship first is designed around relationships instead of data, this 3D aspect comes easy. Now we have the dataset, simple as that, we can add the same filter we had in the SQL before. And lastly, now that we've got the dataset and filtered it to just the nodes we're interested in, we can return the data as our last statement instead of our first. Here, to follow the example, we'll return tabular data, like the SQL was returning. But because we're now working within a paradigm focused on relationships instead of lists, we could just as easily return structured data, including the nested relationships of people. This traversal first language is called Cypher and is one of several graph-oriented languages available. So you see, changing the assumptions underlying the way we store data allows us to change the paradigm and constraints of our interaction with our data too. Aligning our schema primarily around relationships, we're able to use those relationships to both enrich and speed up our data storage and retrieval. So what would we use this database paradigm for? We often hear of graph databases being assumed to be good for social networks, traversing n-deep interpersonal relationships like we saw in our example. And while this is true, we need to remember that rich relationships don't only occur between people. Another place relationships occur is between people and the things they like. And not just the things they like, but between themselves and the things that they might like too. So recommendation systems are more powered by relationships than by the row data they join. Rating systems, either up or down, can greatly enrich the data on those relationships and can help identify similar purchasing traits. Similarly, when someone buys something, that's also a relationship in effect. It's an access relationship between you and your card, and another between your card and the bank. A database that prioritizes these relationships and their traversal makes it easy to do connected analysis on patterns of behavior, which means it's easy to identify fraud patterns and prevent them. A third place where relationships take place is in search. On the surface, we may think of search as returning lists of results, but actually, the way we determine relevant results of anything beyond a simple text search is by following the relationships between topics and tags, and the respective weightings of these, so that we identify the topics that are relevant to the user's search. A fourth place relationships occur is in enterprise dependency modeling. We see dependencies between software components all the time, and it's important to model these successfully in order to refactor systems, and graph databases are useful for modeling them. But we don't need to leave it there, because the dependencies in your systems aren't only between software components, but also between these and people, systems, authorities, sites, files, servers, etc. And being able to model these correctly can help with refactoring, cost analysis, and organizational alignment. And so I'm hoping you can see it's about where both data and relationships are important, but that the relationships are the more important of the two when making decisions, that graph databases are more useful. Yet another place relationships are more primary than data is in permission and access control. While permissions may seem on the surface like lists of data, in practice the simplest way to model a permission system and the groups it contains is via a graph. Evaluation of per-user permissions is then simple via the relationships between a user and an asset, where the type of access can be defined directly on the relationship itself. And so an n-hop traversal through groups is much faster and simpler than a typical relational database model. And there's a theme in all these use cases, so I'll call it out here. When faced with the question of when we should choose a graph database versus another database style, the answer is really this. You should choose a traditional relational database when the lists of data are more important and more likely to be queried. And you should consider a graph database when the relationships are more important to the value and more likely to be queried. To recap then, we've covered now how traditional relational databases are not in fact relational, but that they actually just store lists of data which have lookup IDs to other lists, and how there are additional layers on top of these the database offers in order to support foreign key constraints and joins. We've also discussed how SQL leans on the ability to join tables, but also that joins between lists of data are heavy on compute. And ironically, the SQL paradigm of joining tables causes the heaviest operations for a database storing data lists. But we've seen how these relationships are really important, and so we've talked about the difference between information and knowledge, and how the latter really comes from the relationship between the dots. We've covered how we model nodes and relationships in a graph schema, how we store these, and how a graph database traverses these internally, and the resulting paradigm shift in language we use to query these. And lastly, we've covered a huge range of use cases that are traditionally modeled in tables, but that can be both simpler and more powerful when modeled with richer data on their relationships. I hope you've enjoyed this talk and now are feeling comfortable to explore graph databases more fully.